Okay, good morning, ladies and gentlemen. Let's see what we got going on here. We've got section 3.2, the scalar equation of a line. So already we're off to a brand new start. We got a brand new word in there, the scalar equation of a line, and the normal vector. So these are two things that we're going to have to talk about. Recall from last day, we discussed that in order to determine the equation of a line on a plane, we need either 2 points on the line, in which case we will determine a direction vector and use one of the lines. Using those two pieces of information, put them together for the vector equation of a line. Or 1 point and the direction vector, in which case we don't have to create the direction vector. It's already given to us, and we're good to go. Just checking my desk for my coffee, looking for it, and here it is, and off we go. Okay, what if, instead of giving us the direction vector d, the information provided us with the direction vector that is perpendicular to the line that we are given? So it gives us a direction perpendicular to the given line. So this is very analogous to grade 9 when they gave you someone else's slope and said that the two lines were perpendicular. So a normal vector, we better define that. A normal vector is any vector that's going to be perpendicular to a line is called a normal vector. So any vector that is perpendicular to a line is called a normal vector. Or simply, we'll call it a normal line. Now the reason behind that, looking for a piece of paper here, here we go. The reason behind that is that if I have a line, any vector that's going to be perpendicular to this line, so let's say my vector that's perpendicular to the line is here. Well, that vector can certainly be brought and put here. We would say that that's going to be normal to this line, but then again, if this was another vector that was perpendicular to the line, that one would also be normal to the line. Notice it's going in a different direction, but it's still perpendicular to the line, so therefore it still satisfies our definition of being a normal to the line, a normal vector. And since the vector could continue in any direction, we're not specifying the size of this vector could then be considered a line. So this vector, since it can be a scalar multiple and go as far as we want in this direction, as far as we want in this direction, we could also consider this the normal line, not just a normal vector. So there you go. I got some stuff happening there. Extensions. This vector is like a direction vector, but it's going to be perpendicular in direction to the line. Since the normal is a free vector, any scalar multiple of n will still be perpendicular to the line. Therefore, there's an infinite numbers, and I think we talked about that just now. And this also means that the normal vector can be considered a normal line. And yeah, we definitely just talked about that. So another swig of coffee, and off we go. Okay. Example 1. Determine the normal line to the line 2 comma negative 3 plus t 2 comma 5, where t is an element of the real numbers, which means it's a parametric, it's a parameter. We want to determine the normal line to that line in vector notation using vector math. All right, so this could all be done using grade 9 methods, but we want to use vector math. Then show that these vectors are orthogonal using the dot product. Well, which vectors are orthogonal? The direction vectors that we're looking at. Okay, so let's see. We want the normal line to this line. This line, 2 comma negative 3. 2 comma negative 3, there's my point. And notice that my direction vector is 2 comma 5. Now my direction vector is put here because that's where it would be. 2 from the origin, 5 up from the origin. Okay. However, the direction vector would be applied at this point. And in fact, we would be adding scalar multiples of it, which is creating this line that they've given us. That is this line. Well, the normal to that line would be perpendicular. Now we're supposed to be using vector math to do this. So let's see. Let which will be A comma B, be any, because there's more than one, there's an infinite number, any vector perpendicular to D. So if that's the case, if they are perpendicular, therefore, we know n dot D should equal 0. That's the definition of the dot product. So we know that A comma B dot 2 comma 5 should equal 0. So we get an equation that'll equal 0. Now, this is kind of neat. This means that any value of A and B that satisfy this equation will be a normal vector to this line. So any value of A and B, and they are scalars, that satisfy 2a plus 5b equals 0 will work for a given normal vector. So for example, any value that'll work, -5, if I put it in here, and -5 and +2 will work. Noticing if I put -5 in for A, I get -10. Put in +2, I get 10. -10 plus +10 will give me 0. This is going to be in vector notation using vector math, determine a normal line. This will be my new normal. So using that, I can come up with the line that would be the normal line. A normal line would be choose any point that I want to be on this normal. Now this is here, -5 comma 2. -5 comma 2. Let's put it there. There's my normal. It is perpendicular here, which means that to come up with a normal line that's a free vector, I can place it anywhere I want along this line. I might as well place it here at this point. Why? Because it's just as easy. I know that point. I could figure out another point on that line, but what's the point? It's already there. Haha, get it? What's the point? I know Brienne would like that. Okay, so what's the point? So it's going to be 2 comma -3 plus t -5 comma 2 is my new normal line coming this way. And there you go. Now it says then show that these vectors are orthogonal using the dot product. So what it wants me to do is prove that they're orthogonal, which basically means prove this. So I need a little bit of room off to the side to do that. So I'm going to say, so prove that'll mean that they're going to be orthogonal. And so my n value that I used was -5 comma 2. My direction vector that I had was 2 comma 5. And I'm going to do -10 plus 10 equals 0. 0 equals 0. Therefore, n and d are orthogonal. And we have a proof that went and did that in the last unit that said that if we do the dot product and get a scalar value of 0, therefore the two vectors must be orthogonal. And that's about it for that question. So I'm going to stop the video here so I can start uploading it, because that takes some time, and we'll move on to example 2. Just so that you know, this wasn't the only value I could have come up with. I could have come up with maybe +5 and -2. So another normal that would have been perpendicular here could have been -5 and +2, in which case it would have been, just to see what that would have looked like, -5 and, oh, I shouldn't use blue because I've already got blue on that diagram. Let's use -5 and +2. So, oh wait, I already did negative 5 and positive 2. So what if we did positive 5 and negative 2? So positive 5 and negative 2, that would have been here and here. So positive 5 way out here and negative 2 way down here, and it would have put us here just up above the line, but that vector there, which also would be perpendicular to this line. So hope you see what's going on, and we'll talk more about it later.